Welcome to the meeting 57th of the Junto Club. We are inspired by Benjamin Franklin's original Junto Club, founded about 300 years ago, to discuss topics about science, engineering, business, all kinds of stuff that interests us. And so the goal is to, uh, learn through, and it's for my personal selfish intention is to learn through teaching. So by through talking about what we are reading, topics that interest us, hopefully that we can share and at the same time, learn the topic better. So and the other motivation for me is to actually to improve my communication as well. So every time, well, when I listen to the podcast afterwards, oh man, I was like, oh man, I talk weird, and also the way I say things are always like, not that great. So I always okay, so that's why I want to kind of practice this as well. So so today's topic actually is Claude Shannon. We will talk about who he is, who he was, and how his impact and his contribution, and the main things and how and then lessons we can draw from his life and his work in a way. So to start, we start with a quote, and today's quote is good tests pass, great tests fail. Anonymous. What do you think?
Can you repeat the quote?
Good tests pass, great tests fail.
So, I guess my off the top of my head, it's I'm thinking like so no system is going to be like perfect. Like there
Mm-hmm.
could be points of fault. Like I mean, I guess unless it's like a trivially simple thing. Like if you're doing anything complicated, it's going to have points of fault. So like you're always going to need or going to want to find those points of fault in order to improve the system. So you need to like, you need a test that, identifies where improvements need to be made. If you're just saying like, if you just do the improvements where it's like or like if you just run tests that say like this is good enough and it's like safe or whatever, like the system isn't going to kill anyone, then you're
Mm-hmm.
never going to reach the point where it's like as efficient as possible or whatever the other areas of improvement may be, efficiency, cost, whatever.
Mm-hmm.
That's basically also where my mind first went. Like, oh, a test's failing, identifies, you know, something something missing, something absent. But there's a lot of context of tests, right? Yeah. I mean, you're thinking of like a software engineering test, you have like tests you give like students. And also I was kind of thinking about like a test you might do as part of like a scientific experiment. You might say like a good science experiment, they set up a test to show something and they show it and that's all good. But sometimes in science, like when the most progress has been made has been when something unexpected has happened. The test has failed, something they never realized would happen happened. And then from that, failure, that like not understanding what was going on, people like dug into it and that's led to like a new branch of discoveries and like information. So in that context as well. But at a very high level, it's the same thing, right? Like a test failing can show you that you're missing something, right? Something's missing that you uh, need to learn more about or deal with
Mm-hmm.
appropriately or whatever, depending on your context.
Yep. Exactly. So actually, this even though and this quote is coming from anonymous, actually it's from me. Self-serving.
Nice shoe.
So
Okay.
I come out with it because just doing a lot of robotics stuff in the field, and then a lot of engineering. Sometimes just realize just for the team, right? So a lot of times we conduct a test, and in the field it failed, and we all feel like, oh, okay, this feel kind of like failure, right? Like sucks. Oh, okay, whatever the code you wrote, you know, and then somehow the test, did not pass the test, right? You had to roll back the code and stuff, even for the customer and stuff like that. And I just came out with the quotes just kind of to motivate my team a little bit. And I said, oh, good test fail, I mean, good test passed, right? But great test fail. So yeah, and like you say, you actually detect like failure point, especially for robotics. Like if you working in the field, right, and then something like if you don't catch it, especially safety stuff, like it doesn't catch it in your test, you're actually gonna in a production environment, like real world, you're gonna hit like you're gonna cause disasters situations, when you're working with real humans and stuff like that, right? Around a robot stuff. So that's where it was come from. But I also like your point of view of that. Oh, you sometimes you discover something new when the test actually fails, right? So you discover something unexpected as well. So yeah, and this actually getting line uh exactly. I mean, in line with like what we're talking about, because Claude Shannon, he's I would say one of the greatest scientists of the 20th century, or ever. So
Oh, high praise.
yeah,
All right, hold on. I
yeah,
have one
all
question
right,
for you though.
yes.
Okay, if good tests pass and great tests fail, what do bad tests do?
Oh, bad tests. Great question. No idea. Bad tests just pass too, I guess. You can say that. Yeah,
Bad test doesn't properly characterize the requirements.
yeah. Bad tests pass as well. Bad tests pass too. Sometimes the test pass and it's still bad test, right? So I mean, a lot of times we what do you call that? Like pass something, right? We just want to pass something that just make us feel, sometimes we, whatever. Like some people do some. Depends on incentives, right? I think the main thing, I guess, in the test is the main thing, like the motivation. Why do you do the test, right? A lot of times, like you want to pass a milestone or to meet some kind of criteria, but you lose the context, the goal, the objective, the mission. Then you just let a test pass, right?
Hmm.
And then yeah, that's it. It doesn't catch the stuff. Then you just flow through, and then the project ending failure, right? So I guess a back test on on the one actually passed, but end up in disaster. You discovered it in a in a real world, like bridge collapse or stuff like that, right?
Mm. Bad
Uh,
tests pass
yeah,
but hide something important.
yeah. That's the worst. That's the worst. Actually, that's the worst thing. Worst test.
Yes, good
Yeah,
tests. Good
yeah.
tests
That's why I'm.
perhaps, but hide things that are less important. And
Yeah,
great
yes,
tests reveal it all.
yeah. And that's why I always worry about. I always try uh to ask the engineers what kind of thing they are testing. Like what kind of stuff they are try to how they try to test, and then how do they stress test the system, right? Because they always bug in the system, and how you try to capture prevent a catastrophic failure. Because actually those happened to me before, so that's how I kind of think about testing, right? So. And I also that's why I try to encourage the teams that okay, don't try to make sure the stress test every single thing, especially in the most catastrophic failures.
Hmm.
Yeah, yeah,
You could say tests are trying to provide some amount of information, and if only there's a way to quantify how much
information.
information could be sent.
Yeah, exactly. Wow, that go right straight into information theory. Nice
Totally
pivot.
random. Not didn't bring that up for any particular reason. So anyway,
Yeah.
Claude Shannon.
Uh-huh. Okay. All right. So let's get into it then. So Claude Shannon. So my first question for you guys: do you guys know who is Claude Shannon?
I've heard of Shannon's information theorem, but I don't really remember what it was exactly or much about it. So it's only like a vague thing from school days that I know someone told me once.
Okay. What about you, Mike?
Yeah, I would say same thing. I don't know the man. I know
Okay.
I
Okay.
pretend
All
to
right.
know the
Yeah, yeah.
math.
Yeah, most people like know has studied his work before, but actually don't know his name. Like we know about information theory. And what about man? Let me ask you. So you say study kind of know maybe aware of information theory a little bit. Like, do you have any? mm, Do you know what exactly is information theory? maybe just describe what you know. Like,
Uh, well, I thought Shannon's information theorem was something about like signaling or like sending information. When you
mm-hmm.
talk about information theory, that usually makes me go to like expectation maximization algorithms. I'm not even sure if that's accurate
Yeah.
though.
Mm-hmm.
Which are just, it's kind of like any sort of optimization or gradient descent, right? Where you're just trying to like tune something to be better, um,
Yep.
changing it and testing it. But expectation maximizations, using some smart math behind it to try to do it in an optimal way instead of instead of like a dumb gradient descent where you just sort of arbitrarily move.
Mm-hmm. Yeah. Yeah. All these are actually AI. Current AI stuff is like even your maximization, optimization stuff. It's very much like draw from Shannon's theory of, information theory. So that's why I'm very excited to study him too, because currently, AI is like blowing up, right? So,
Hmm.
but Shannon actually have been, study that for a long time, and then a lot of recent, stuff is very much based on. So his influence on AI. So it's good if you want to understand AI. Yeah, I think we should go back and study Claude Shannon.
Are we going to get into some math today? Shu, is this going to be a hard lesson of Junto?
A little bit if you want to, but not probably not. Because I don't really understand it myself. I'm still digesting it a little bit. So, what about you, Matt? Oh, Mike, any thoughts?
No, I mean,
Oh,
when you say information theory, like, I mean, what Matt said, but I guess also thinking about just how to represent information. So, like,
mm-hmm. Yeah,
sort of how can you represent information as efficiently as possible, and like
exactly.
like what number of bits, like, I mean, if you just
Mm-hmm.
want to go directly to sort of the computer science, like, how many bits does it take to represent, like these number of
Exactly.
things? Yeah.
Have you, computer science, have you heard of the parity coding, stuff like that, the parity bits, stuff like
Yes,
that?
you're going back to my undergrad show.
Exactly.
That's quite some
That's
time ago, but yes,
That's
I have.
directly from. I mean, Shannon did not like create that parity like scheme code directly, but this is directly based on came out of his theory, right?
Mhm.
And then Mike, since you are electrical engineering background, have you ever studied logic gates?
Me,
I mean,
well,
even Mike, right? It's a logic
yeah, yeah,
gates, right?
yeah,
N
yeah,
gate, OR gate, NOR gate,
yeah.
digital
No, no,
logic stuff.
like, I mean, you and Matt have much more hardware experience than I do,
Yes,
but that was literally like the only thing we had to do was build like like use like we had to use a breadboard and build
yes.
some type of like like some
Mm-hmm.
type of adder subtractor type, like that was the only hardware I had as
Yep. Mm-hmm. All net is from Actually, that is from Shannon's master thesis. So Ned,
He did
using
a
that,
bitwise adder subtractor. He created that.
yes. So
Ooh.
what do you call that? So his master thesis has been called the most famous or the most important master thesis of all time. So we'll get into that later. But
I mean,
yes,
yeah, that's like a foundation of computers, right?
yeah.
So,
exactly. So that's why I'm very excited to study him too. It's like foundation of everything. All right. So to back to the intro. Claude Shannon was an American mathematician, electrical engineer, computer scientist, cryptographer, an inventor known as the father of information age. Shannon was the first to describe the Boolean gates, electronic circuits that are essential to all digital electronic circuits, and was one of the founding fathers of artificial intelligence. And that is came from Wikipedia. And then the other source, now I drew most of the content. I mean, from it, I read a book called A Mind and Play, basically a biography of Claude Shannon. And as we talk, you know why in the title A Mind and Play, it will become very apparent to you. And here's from the book. Shannon had done what practically no one else had done since the Renaissance. He has single-handedly invented an important new science. Shannon's information theory is an abstract science of communication that lies behind computers, the internet, and all digital media. it is said that it's one of the few times in history where somebody found in the field, asked all the right questions, and proved most of them and answered them all at once. There were many who compared Shannon's insight to Einstein's. Others found that comparison unfair to Shannon. Einstein's work had virtually no effect on the life of average human beings. The consequences of Shannon's work were already being felt in the 1950s. In our digital age, people ask to characterize Shannon's achievement are apt to be at a loss for words. It's like saying how much influence the inventor of the alphabet has had on literature. It was Shannon who had an idea that computers should compute using the now familiar binary bits, 0 and 1. He described how these binary numbers could be represented in electron circuits. A wire with the electrical impulse represents 1, and wire without impulse represents 0. Anyway, so yeah, I think this is what we talked about already, right? And the numerical code may convey words, pictures, anything. And then let me see, turn out so in the 60s, 70s, 80s, right? A year went by, not scarcely a year went by without a digital trend that made Claude Shannon more relevant than ever. Right? The transistor, the integrated circuit, personal computers, and now the AI, right? So that's why anyway, I mentioned it already, and that's why I'm excited to study about Shannon. So yeah. So you were shaking your head when you was comparing Einstein, right? Yeah, it was very extreme. I think also kind of,
Well,
saying that Einstein's work has no impact on every
yeah,
human being, but yeah,
that's not really quite accurate. Now, I
yes,
would agree based, on what I've heard so far that, if you're going to ascribe, computing technology to Shannon in general, obviously that's had more of an impact than Einstein's work, but Einstein's work has certainly had impacts.
on everyday
Like,
life,
sorry, what?
on everyday life, human being.
Yeah. Do you enjoy using GPS?
Yes, yeah, as
Well,
you mentioned it
GPS
before,
only
relativity. Yeah.
Yeah, GPS only works because we can calculate the time dilation using relativity. So,
What
and there's
else?
like,
What
what
else?
else? Oh man, how many do I have to have offhand? He was, I believe Einstein was the one who discovered didn't he discover the photoelectric effect that to
Probably.
which is like the foundation of photovoltaics.
Yeah, yeah.
So, solar
Yeah,
panels?
yeah, and it's just an extreme comparison. So yeah,
Yeah, yeah.
but, but
He's just saying no influence at all. Unless that was supposed to be in 1950,
yeah,
maybe his
yeah,
things hadn't had as much
but
of an
not.
impact
I
in
mean, may
1930s.
not. So what? Here's the comparison, right? So no Shannon. Do you like Netflix?
Yes.
Yes, no Shannon. I would say no Shannon, no Netflix.
Oh
So that
man,
is a huge impact, right?
no
So
online video
how
games. Come
I
on
mean,
now.
how can you say no Einstein, no internet? I mean, sorry, no internet, no Netflix, not
No,
Netflix and chill. So
Netflix and chill.
yeah,
No, but you'd have to pull out your maps on your road trip still, and be like, ugh, where am I?
yeah, I'd rather live with that than without no streaming. I guess no Netflix. I think most people will agree.
Okay, okay. We don't have to fight over geniuses.
Yeah,
Who's the biggest genius?
yeah, yeah. All right. What do you think? You got any thoughts on Mike?
No, I mean, I was just thinking about like how I don't know. I mean, I feel like the internet there is some way, no matter how indirect, in which like like the internet depended on GPS, or like
Mm-hmm.
like the current form of things depended on
Yeah.
GPS. So,
But yeah, I mean, yeah, yeah. I think they try to just make it, make. I think because, okay, I think he is my thought on Shannon too, because he's the most I feel like he's the most underrated scientist of the 20th century. Like everybody know Einstein, everybody know about Newton, but
Mhm.
right now on the foundation, everything we have, internet, iPhone, all because of Shannon's theory, information theory, and all digital computer because of his master thesis, right?
right.
And
Mhm.
then by most, he's almost like forgotten in a way, right? So even though his theory, we still study theory, but his name is just not like in the same, same league as like Einstein and Newton, right? So I think that's
Hmm.
why the author is to make an extreme comparison, right? So
Hmm.
how impactful his work is. And the last point I want to make is that actually recently AI, even if without China, actually I don't think there's the AI revolution is going to be here right now. And then not sure ChatGPT going to be actually possible. And one of the reasons you can see his citation. So in 2017, the book was published, and he say, "Oh, no, his information theory, the work was cited like 90,000 times." And then I look at it today. Actually, the number had doubled in the past 5 years, even though the information theory was published in like 1948, in the 50s. And the
Hmm.
reason, one of the main reasons, is because machine learning. Uh, I think 720. And you mentioned maximization, whatever stuff that you mentioned earlier, right? Algorithm. If I look at like 2024, you look at it was cited like almost like 8,000 times by 8,000 papers. And then you can see all the papers was actually a lot of papers were titled like something like Gemini, something, and a large language model and multimodal stuff. So all recently like it's all the AI papers are cited cite information theory as a foundation, right? So anyway, so
So what you're telling me is all the uh, AI written papers are citing their father.
exactly. Anyway, yeah, you're right. Yeah. He funny. He actually organized the first AI conference in the 1950 or 60s. I don't remember. Yeah, back in the day.
All
All
right.
right.
So I feel like you've been teasing us for long enough. What is Shannon's information theory? What is the core principles underlying it?
Okay. All right. Sure. All right. I was thinking of going through his master's thesis first, but I guess we can go straight to his.
We okay, never. We can do his master's thesis first. That's fine. That's fine.
Okay.
Don't
Sounds
let
good.
me get you off track.
Yeah. Okay. Sounds good. All right. I think there's a relation between his master's thesis and his. So, all right. So back in the day, right? You before so basically his method is laid out as we talked about earlier, like using logic gates, right? To build logic gates basically, and then to use his most significant, I would say, I guess, impact on the theory from his thesis that to using one and zero to represent using actually not using one and zero, sorry, it's using by Boolean algebra to represent to build circuits basically. Now all circuits can be represented using uh represent to describe the circuit using Boolean algebra. So logic gates, right? And you
Mhm.
can basically he's married Boolean algebra and electrical engineering, math and electrical engineering, right? Because back in the and then also using one and zero to when a circuit is on, right? One is like because the Boolean algebra is like is one and zero, and then he said when the circuit is on is one and off is zero, and then Boolean algebra that's what it does is just one and zero, right? And so before before Shannon's master thesis, like all the circuits, like the way we design engineers design circuits, very like trial error, right? You design a circuit to represent something to make this, for example, I think to solve an equation, right? Someone will build a circuit, right, and then using trial error to make the circuit work, and then the circuit could be very complex, right? Could be maybe you need many switches or something, right? But because of if you using a mathematical model and a Boolean algebra to describe the function you want to do, and you describe the circuit in a paper, and then you can actually simplify using Boolean algebra. You can simplify the circuit down to the very minimal equation, and then you third step, the last stage, you build your circuit using that equation.
Mhm.
And that way, because before that is always trial error, so you all very complex. Now you just need, before you actually build a circuit, you actually, draw it out in paper and then you design it, right?
Hmm.
So that's when the AND gates and NOR gates and if gates and all this stuff is actually basically is the fundamental elements of the what do you call that? Digital age, right? Mike, you have anything else, Matt?
I'll rephrase it because I feel like this is somewhat intuitive me because I have an electrical engineering background, so I've like used Boolean algebra and stuff. But if you're a hypothetical listener who's never
Mm-hmm.
done that, right, you could imagine like, someone makes two circuits that do two specific things and then they combines them together.
Mm-hmm.
So, that creates a larger, more complex circuit. This allowed them to basically write that as a equation that adds those two circuits as their own equations together. And then you could say, just like in algebra and regular class, you can go through the math and say, wait, can I simplify out parts, cancel things out, reduce it down to a simpler function that does the exact same thing, has the
Yeah.
same mapping of inputs to outputs specifically.
Okay.
Yeah.
Yeah.
And then that makes it easier to build.
Okay. Sounds good. Personal experience. So have you guys studying like, logic, in what do you call that? In
School.
college, right? In undergrad, right?
Yeah.
How would you experience when you first took it? How did you, was it like foreign to you? Was it like hard to grasp? Or is it easy for you to grasp?
I feel like it wasn't that bad, but I mean, I remember even as like a kid in like, regular public school before college, there was stuff like,
Mhm.
what is it they called? There's some sort of like Boolean search things. I remember we taught once for Google. They're like, you say like search for this and this, or search for this or this,
I was
things
thinking
like that.
Excel. Like I took like in high school, I took a class that was like basically like how to like it sort of was the class like I feel like they say people should take now, like how to manage money, like thinking about retirement. Like and like and I can remember like I had to write some type of like do some type of Excel sheet for budgeting, and we use like sort of conditional statements and exactly what you're talking about, like and or type statements. So
Yeah, I guess in modern day, this is not to diminish the work of like founding this field, right? But now in modern day, these concepts are so widespread. It's not as it doesn't feel as revolutionary, I guess, because it touches on things all the time.
mhm.
Mm-hmm. Yeah. Oh, funny you talk about finance because another reason we're studying Shannon is because he's one of the best investor of all time. But yeah, we will talk about that too. How he, yeah. Um, so one of the reason I asked you that because when I first took digital logic in undergrad, I was super confused actually. No, it was very hard for me to grasp it, and I actually have to drop out the class and took it a second time, and then second time is really. I remember I went to like one professor's class, and he was just explaining the gates, logic gates to me, and he said, "Oh, see the power switch here? You turn the lights on. That's one, off is zero, and stuff." He just explained some of the stuff that using that. I was okay, still, and then yeah, so anyway, that I had a hard time with it because I did not have the Boolean algebra background, or just maybe not as logical as as thought I was. So
You
yeah,
didn't grow up with computers when you were young,
yeah,
right?
not as much. Yeah, yeah, yeah. And then so another thing is another impact of this is that uh before one of the reasons that Claude Shannon arrived on this problem is because he was working on something called at MIT, something called differential analyzer. It's very much a mechanical computer. On the gears, on the equation, fixing the circuits, instead of electric circuits, like logic gates, computer is actually everything is mechanical links. And then it takes like 4 days. If you have a problem, want a computer to answer, you actually Carl Shannon have to like disassemble all his mechanical stuff and then assemble it again, which takes like days. And then you put through the problem, it's gonna take another day's compute and a few days to come out with the result. So that's as you can imagine, that he probably had a lot of time to think as he was like working on this, and then to happenstance that he actually as he's actually studied since in undergrad he was studying like because he both interested in math engineering. He don't know can decide what to study, so he studied both engineering and math. And one of the class he took was Boolean algebra. And as he was in MIT doing his master uh, degree, he actually gained an insight of marrying both like Boolean algebra and circuits. And then also I think another important thing is that since you can use Boolean algebra, it means the circuit that the switch doesn't matter what it is anymore. It doesn't have to be mechanical. It could be like it could be anything. It doesn't even have to be electrical, right? Why does it? Because as long as you can represent gates, right? Because right now we are limited to electrical circuits because that's what we have. It's the best so far, right? But and that's why it became mechanic vacuum tubes and transistors, and right now we still have transistor. So that means something else could potentially replace the transistor, right? So if you look at the chips like GPU from the NVIDIA and stuff like that, so that's another implication that of what could I don't know computation can still be changed, but the theory still stays the same, right? So anyway, cool. And so yeah, that's one of the lessons. I guess before I move on, is the lesson I guess I took away from this is Claude Shannon actually is very like just very much follow his like curiosity, and then he just like a lot of times like you want to specialize in one field, but the idea is that maybe it's better to study multiple fields. That way you can actually take one idea from another field and then marry them together, and then yeah. So all right, I guess it's time for information theory.
Okay. The appetizer has been eaten to the main course.
All right. So yeah. So the information theory basically there are three questions that Shannon was asking for the problem he was thinking about when he was came out with the information theory. So the three questions he asked like how information is measured, like what is information, right? And how can information be transmitted efficiently? I think Mike you mentioned that earlier.
Mhm.
And then how to transmit like message like despite of noise, right? Because every communication channel is noisy. And how do you do that, right? If so, yeah. So before I move on, like what's the definition of the information? Like what is information? That if you if I ask you that to you, what would you say? What is information?
Maybe I'd try to say something like data with context.
Data with context.
Yeah,
So
I was thinking something that was mutually understood. So,
Mutually
as
understood.
I guess data, is just like a basic, like you imagine there's just like, what memory holding ones and zeros, right? Bits in a computer. But that could be all data, but without the context to read it, to understand, to interpret it, it doesn't really give you anything. So is that information? Maybe you would need both. I don't know. It's a very hard question.
Okay. Data with context. That's your proposal.
Yeah.
Okay. Mike, did you say something?
yeah, yeah. I mean, I like. Well, when Matt said that, I was thinking so. Like before, I was thinking something that's mutually understood, which is very
Mutually
similar, I
understood.
guess, because like basically you both like again. I guess I'm thinking of yeah, sort of two computers, two people, sort of at the end of some type of communication link. Like they have some pre-existing knowledge about how to interpret what the other sends. And what the other sends, like it can come in many different forms. It can come as ones and zeros. It can come, I guess if you're literally just talking to each other, it can come as some type of utterances, that in theory your brain isn't exactly picking up as ones and zeros. Like, but there's the like you each do have that context, right? Or, the
Hmm.
mutual understanding of like, okay, this, whether it's grunts or English, that's what this means. Or if it's ones and zeros, the computer can display it, because the same type of, standard is being applied to those ones and zeros. So,
Mm. Sounds like you're talking about like mutually understood, like something is more like predictable in a way. Like you, I mean, mutually understood, that means like you can kind of predict
yeah,
and have a
yes.
certain rule to apply to the information, right?
Essentially, yes, there's some type of standard, yeah, to apply to the information or to apply to whatever is sent.
Hmm. I
It's not
see.
just like random, or it's not just what you otherwise like you. It's not like this is just the first time this type of interaction has ever occurred. Like there's some
Hmm.
pattern, like I guess that would have emerged before that allows for
Okay.
you know a, you to interpret what. Yeah, I mean, I guess I'm thinking back to like the first, the like where language is born or whatever, and it's like, oh, every time they point at that tree, I notice, he comes back with like a squirrel for food. Like, so him pointing at that tree means it's like there's squirrels there for food or whatever. I don't.
Hmm. What about meaning in information?
Meaning in
Meaning?
info.
Is
Yeah.
this
I mean, that does information have anything to do with meaning?
yes? Because I think that's where sort of where I was trying to go with like context and stuff. Because if you just think of like a basic wire, right? Like, well, think of like Morse code, right? Like, Morse code's kind of ones and zeros. It's dots and dashes, I guess, and you have the spaces. But like, whether it's Morse code or it's just literally zeros and ones through a wire, like you can't like that's not enough, right? Like the raw data isn't enough. You need agreed set upon rules on how to interpret that, whether that's like the Morse code itself or whatever message format your computer's interpreting it as, right? Because those ones
Hmm.
and zeros could be, are those colors for pixels to make a video? Are they, characters in a string you're going to print out? Is it something else? Like, um, so there's more to it than just the raw data. There's the context, the meaning, the mutual understanding that Michael was talking about, right? So that's like equally important,
Hmm.
and something being like information in a meaningful sense.
Okay. Sounds good. Um, yeah. So I think Shannon would say, yeah, information has nothing to do with meaning, but I think that's a little bit different. I think what you are thinking a little bit different about like how do you decode once the information is sent over a communication channel, and how do you decode it in the end? Which means you have something that agree upon, right? But yeah, that is how that kind of method, is done through his theory, but basically he arrived at that by ignoring the meanings and stuff like that. Now, how do you measure information actually, right? And that's one thing that because you need to define what is information. And then if you define information, if you have meaning in that kind of information, then how do you measure information? That means you need to measure meaning or something like that, right? So either way, so I think what he arrived at information is something about is resolution of certain kind of uncertainty. So, for example, you flip a coin, right? It's 50-50. You have some information, and you have weighted info. If you weighted coin, which is like certain, right? Which is like 90% of the time you're gonna land it on tail. net has less information compared to the randomness of the 50-50 because weighted point is more certain, something is more certain has less information. Something is less certain, you have once if net is communicated, right, it has more information, right? So it's almost so I guess the information has something to do with about the message is uh probability of that voice communicated using that message. Like, yeah, right. Now, for example, if we all know Trump is going to win, right, then the result of the election has no information because we already know Trump is going to win, right?
Mm.
And then if we don't know it's a toss, then the election will convey more information, right?
I have an excellent example of this.
Okay.
Are y'all familiar with ELO from chess? Like the ratings of players and how they like the rating changes as they play each other. Have you ever heard of this?
No.
Say it again.
ELO?
Elo?
Yeah.
No. What was that?
Oh man, you guys never play video games. Okay. Very quick detour. ELO is like chess players just get a number, and basically when you play each other, the winner's number goes up, the loser's number goes down. Um, this is like the basis of ranking systems, and like most video games now use matchmaking ratings that are sort of based on ELO but more complex. But it has that core idea. Like if two people are rated the same and they play each other, then the winner is going to go up by some jump because that's like an uncertain event. So you're saying, that seems to give us information that this player, there's a good chance they're better, right? They won. If you had a
Mm-hmm.
really good player play against a really bad player, right, and then he wins, he's just going to barely move if at all, right? Like there's an equation that says like, how much you adjust is based on that difference, and it's hardly going to move because you're not getting information, right? You knew this guy was better than the other player because he's rated way higher, right? So that event was very expected. Thus, it doesn't give you any information. Thus, it doesn't change their ratings. So that's exactly what you're talking about in the video. And comes up
Mm.
in video game stuff a lot. So that's why I'm like, that's that. But
Okay. Nice.
okay,
Good
anyway,
example.
maybe
Yeah.
maybe that's a good example for someone, not y'all, but
Yeah. All right.
okay.
Mike, you got any thoughts?
Uh, I mean, I guess I go back to like this has nothing to do with meaning. I mean, or and I guess the way we're using information and stuff maybe differently, but or like I guess the technical use of these terms can be like obscured a little bit here. But
Mm-hmm. Semantics.
like, I mean, to me, it's like it makes sense that like okay, in your example, like yeah, or I guess we'll go to Matt's example of the video game because I did get where it was coming from. Like if it was essentially assured that like one person would beat the other, then that doesn't necessarily have a whole lot of meaning, right? Like or like a whole lot like it gives us very little information because we sort of knew like both parties sort of knew what was up, I guess,
Mm-hmm.
for lack of a better way of saying it. Like, or if we go to the election, if everyone knew Trump was going to win, like that doesn't give the country information. And like there isn't much meaning to the election at all. So
Mm-hmm.
it's like, so I guess in my mind, like the amount of information required, like, I guess the more options there are, like in a way, the more meaning, like the way in which that stuff is transmitted has and the more information is required. Like if there's only one option, there's no like, and everyone knows that's the only option, there's no real meaning because
Mm-hmm.
everyone's on the same page. If
Mm-hmm.
there's, or if one is like far more weighted heavily, whereas if there's like two equally weighted options, then it does like the communication itself has meaning because like it's a 50-50. You
Mm-hmm.
don't know which one it is. So I
Yeah.
guess like if we're defining meaning in that way, I
Mm.
guess there is meaning within the information.
Yes. Yeah, it depends. Yeah. I see what you're saying. Depends how to, I mean, how do you use the word, I guess, right?
Yeah, yeah,
Yeah. But yeah, anyway, so I think next let me so back to yeah, so so that is his one of the most important fun theorem. I think the second theorem of his is to measure uh the right information like relate to uncertainty, and using basically propose using entropy to measure uncertainty. And or randomness of set of possible messages, right? The more uncertain or unpredictable system, the higher the entropy, right? And then there's a mathematical equation that we don't need to go through that, sum something up and then we log something, log two. I haven't done a log two in a long time, but anyway, um,
Well, it's
so
binary. Come on.
yeah, this is very actually very related to entropy. It's very related to. I think that's why is information is very relevant to AI now because our the algorithm try to basically what do you call that minimize entropy, right? It's entropy when you like calculate what's the predictable like yeah, I mean on the chat GPT we talked about that before is all it does is just predict the next word and then come out with message, right? But that's what it does. It try to pick the word has the least amount of uncertainty, right? Minimize the entropy and then give you the answer, right? uh Let me read a quote from the book. So the question that all of Shannon's predecessors tried to tackle was, what is the substance of a message? The essential part that can be dispensed with. To most, the answer was meaning. You can squeeze anything out of a message except meaning. Without meaning, there's no communication. Shannon's most radical insight was that meaning is irrelevant. Shannon's concept of formation is instead tied to chance. This is not just because noise randomly scrambles messages. Information exists only when the sender is saying something that the recipient doesn't already know and can't predict. Because true information is unpredictable. It is essentially a series of random events like spins of a roulette wheel or rolls of dice. If meaning is excluded from Shannon's theory, what is the incomprehensible substance that exists in every message? Shannon concluded that this substance can be described in statistical terms. It has only to do with how unpredictable the string of symbols composing the message is. Right? In real conversation, we always try to outguess each other. We have a continuous updated sense of where the conversation is going, what is likely to be said next, and what will be a complete non sequitur. And the more improbable the message, the less comprehensible it is, and the more bandwidth it requires. This is Shannon's point. The essence of message is in its improbability. Um, so I guess it kind of, like if you try to communication, it's theory of communication, right? Information. So you're sending something to the other, right, receiver. Like why use the effort? Why you communicate if the other person already know what you're gonna communicate, right? So there's no point in communication if it's not if you already know what the message is gonna be, right? So so yeah, anyway, so
Yeah.
all right. So going back to the other, so the definition of, I guess, based on his is a probability. Everything is related to probability. The uncertainty information is the resolution. I think he has a quote that information is the resolution of uncertainty, right? And the uncertainty basically is measured by entropy. That's what he's, I think, second theory or first theory. But before that, another main contribution of the information theory is the bits. So what now you how do you represent information, right? And he proposed the unit of information is the concept of bits, right? We talked about before in the circuit is 1, 0. And there's an interesting story where in uh hold on. Yes. there's an interesting story like, in 1943 where like Alan Turing like visited Bell Lab and Shannon was working in Bell Lab while he was working on the theory. And then Turing and Shannon actually spoke daily in cafeteria, and Shannon informed Turing that he was working on a way of measuring information. He used a unit called a bit, and then Shannon credited the name to another Bell Lab mathematician. But anyway, and then actually, and Shannon defined a bit as the amount of information needed to distinguish between two equally likely outcomes. And then Turing actually told Shannon that he actually have another idea for a unit called BAN, like BAN, that for information. But so it's but it was a bit, not a band that changed the world. It's quote in the book. So so anyway, I think at least I'm glad that it's not banned, but big seems to be pretty good. And then, I forgot. I think the book mentioned like what's the Turing's idea of the ban is something to do with formation, but I don't remember what he would try to measure using the word ban, but
Mm.
something related to information. Yeah.
Yeah.
All right.
Nothing to
Let
do with
me read
bandwidth.
what?
There's nothing to do with bandwidth, I imagine.
Not sure. Could be. Yeah. Let me read this one if this one's useful. If not, I can cut it out. So, the information content of message he proposed had nothing to do with its content, but simply with the number of ones and zeros that it takes to transmit it. This was a jarring notion to a generation of engineers who were accustomed to thinking of communication in terms of sending electromagnetic waveforms down a wire. Nobody had come close to this idea before. This was not something somebody else would have done for a very long time. Okay, so this from the book, I think this just so I think it's also useful to understand like how communication was done before Shannon come up with the theory of using binary bits, right? So that means like before Shannon information theory, all engineers tried information like telephone signals is always like sending electric waveform through wires, right? And
Yeah.
how to overcome noise, the engineer basically just like, the only solution is actually increase the power, like just blast it. Like all the engineers, okay, yeah. And then also they tried, a lot of trial errors. I think that's also in the book. There's a story about I tried to there's a project was to lay in a wire, like telephone calls through the Atlantic underneath the ocean, right? And it was terrible. It was just like not very well done because all they have is like sending the power through, just increasing the power, but the wire need to travel so far, and then is the wire is also very immune to not immune was like very susceptible to noise and stuff like that, broken wires and stuff like that. So anyway, so that was bef and also another I think significant impact of the theory is that using one and zero now similar to the circuits, right? Now you don't care about what kind of medium, like what kind of chain medium you send through, right? Anything can be representing one and zeros as a information, right? Images, medias, whatever, like television, streaming, movies and stuff like that. It doesn't matter what kind of medium you're sending through, right? As long as you can represent one and zeros, right? It can be so it's almost like holistic encompass on how what do you call that? Like you getting into the essence of the message. Like it's almost like you have. Anyway, I actually not sure how to describe it, but maybe you guys have a better way. I guess I'm trying to say like right now it doesn't matter like similar to circuits, right? It doesn't matter what kind of like, how you represent one zero, either transistor or something else, right? You
Hmm.
have this, you take the theory, then you can just create other things as technology get better. It doesn't matter what kind of information you try to think through in the future, right? Because I don't think we have movie because information can gonna be evolved too, right? It could be movies, something else in the future, right? Cryptocurrency, stuff like that. So anyway, so
So this is, I mean, we're basically talking about like analog versus digital, right? Like
Mm.
engineers, when you're saying they were sending information, through wires,
Mm-hmm.
not as ones and zeros, they were sending analog information, right? Analog
Mm-hmm.
radio, analog TV, analog sound. And I would
Yeah.
say that, I mean, obviously there are massive advantages to digital information. Like now we use digital radio, right? Like we use radio waves are sending ones and zeros, and that gives you like cleaner,
Mm-hmm.
transmission, and I think they can pump more data into it even. Um, but to be fair to analog, though, it's not inherently dependent on electrical signals. It's just that is also just the by far the most convenient medium. But I mean, a record, right? A record
Mm-hmm.
in a classic record player, that is analog information literally etched into the physical, the physical material of the disc, right?
Mm-hmm.
That is what is being held there, which is quite interesting. But yeah, it's a very, I don't know, it's like a whole different way to represent the information.
Yeah. What you try to say?
I don't know.
Oh, I thought you
I'm
were gonna
just
say something
rambling.
about benefits of like maybe still analog is still relevant. I mean, I think it's still relevant, but I'm saying I thought that's
Yeah,
your
I mean,
point.
there are niche things that are analog. There are people who are trying to make analog computers for like specific tasks.
Mm-hmm.
But noise is a problem with those. So like
Yes.
analog computers like inherently sort of like amplify noise as the process goes on.
Mm-hmm.
So I mean it's pretty clear at this point, right, that like digital signals are like far superior for the vast majority of tasks people care
Yeah.
about.
Yeah.
Um, I just wanted to phrase it because I feel like we were talking about it without using the words like digital versus analog, but like that's
Yeah.
what we're talking about.
That's good. That's good.
Yeah,
Yeah.
and two, I just thought it was interesting that analog can also have other mediums as well, right? Like that. Those were my only 2 points.
Yeah. No, that's good. I like it. Yeah. Yeah. Mm-hmm.
So
Cool.
what is writing? What is human writing? What would you say it is?
Human writing.
Yeah,
Hmm. Analog.
I
You
would
mean
say
writing?
digital, right?
Just
It's like
writing in
discrete
papers?
symbols. Yeah, it's discrete symbols on paper, right? So is that at its core? Is that really a digital way of conveying information? Human like text?
Hmm. I think you're saying is basically characters like in a different. You basically pick like A, B. Yeah, actually, yeah, you're right. It is digital. It's just very discrete, right? And you have A, B, C, D, right? And those are whereas like, but I think is one. So information. I mean, it doesn't matter how you represent information on language, right? And the alphabet just one way to represent information, and Shannon's point is that I guess his theory, the information theory, is just that almost like get information down to a very fundamental, elemental level, just one and zero, right?
Hmm.
Because you can use one and zero to represent A, B, C, D as well, alphabets, right?
Yeah, yeah.
Um,
It's just alphabet's just a little more convenient for us, but
yeah,
it maps one to one, right? You could map every letter
yeah,
to bits back and forth.
yeah, yeah,
Now,
yeah,
now when you think about it, as long as
yeah.
I'm rambling here, speech I would
Go
say
ahead.
is mostly the same as text in that you're
Yeah,
attempting to resolve the sounds to specific symbols,
uh-huh,
which you could be like say mapped to ones and zeros. But speech also carries this like things like tones,
uh-huh,
um, and subtler information, right? Like
yeah,
um, so is that analog information layered on top of the digital information of the specific words you're saying, but you can say it, in a different way,
uh-huh,
then there's no discrete like, oh, he used this tone, right? It's very much like a sliding scale of like, did he sound angrier or did he sound
uh-huh,
like happier? Like
yeah,
it's kind of
yeah.
interesting.
Mm-hmm. Yeah, and that's why, like a lot, what do you call that? Like the digital information is just a reconstruction of the like analog information you was in of the real world, right? Or I think digital, I think it's approximation, right? You have analog signal, like your voice, your tone, right? And then you record it into that digital format. Then you play it out in end. But that's why still people still like to go to concerts, right? Because you kind of have even though right now it's probably there's no difference, but you still there's some information that's lost, right? When you
Mhm.
transmit it into the digital, right? So I think that's a fair point
Mhm.
too. Yeah. Anyways, yeah, that's good. Good segue. Anything else you want to ramble on? I like your
No,
rambling.
that's enough for me. Do you want to take a turn rambling, Mike?
No, that's all right. I guess just been thinking about like sort of I've been stuck on the meaning point a little bit. Like saying like meaning that like the meaning doesn't matter because it's like I would yes, it's true you can represent anything with zeros and ones, but I would contend that like the whole point is how many bits do you need to represent the outcomes. And I would
Hmm.
say that like when you're designing like an application or something, like you need to define like sort of like literally the precision of like the numbers you're using or some like so I mean like when you're actually designing a system that is intended to communicate information or is going to make use of information, like you're using the context of like how that system will be applied to like I guess define like what how many bits needs to represent stuff. So I mean, I guess the fact that you're using context there, like I feel like you're injecting meaning, like or the meaning is informing the representation.
So yeah, any I'm not. Yeah, Matt, you have any thoughts on what Mike say? Because I don't completely comprehend. So I guess your message is very has a lot of information because it's hard for me to comprehend. It's hard for me to comprehend. So,
Well, I mean, I guess
Matt, do you have what's your thought on what Mike say?
I mean, I agree with Mike, but I'm trying to, you know, combine that with what we're talking about here. Maybe it's just that Shannon's trying to talk about it on like sort of like one level lower, like a bit more
Hmm.
fundamental, like
because it's zero and ones, it's like it can represent anything, so it doesn't matter what it's representing.
Yeah.
yeah, maybe it's like that. And then yes, at a practical level, you have to go one step further and say like, okay, now it's not just about reducing uncertainty, like to be able to, I have to know, it's not about, I have to know, not just know that the coin flip turned out 0 or 1. I have to know was 0 tails or 0 heads, right? Like, but
Yeah,
for Shannon, he's like, well, it can either be 0 or 1. It doesn't matter. Like the mapping doesn't matter. As like a trivial example, right? So maybe that's how it was being interpreted.
Yeah. I mean, I think for information is probably a lower level than like, for example, like intelligence and meaning, right? Meanings could be, I don't know, subjective, different, interpreted differently, more perception based. I think that's why he didn't call it a theory of intelligence because he actually, when he tried to come up with a name for his theory, actually I think, you know, some people try to suggest, oh, maybe intelligence, theory of intelligence, something like that, right? So, and actually, and then that's why, but it still be used by people still could rebel with it. Intelligence very loosey goosey. I don't know what intelligence means. Actually, that's another question I want to ask you. Actually, is like so Shannon, kind of distill information down to the elemental level, right? Like one zeros. But then, do we have a like elemental elements of intelligence? Like, I guess one of the question I was going to ask you. This more like tangent. Like, what is intelligence, right? Uh, what is
You're just
intelligent?
you're just hitting us with lots of easy questions today, aren't you?
oh
And
man,
then, and
I
then,
think
and then,
I
as I
remember
yeah,
when
go
that
ahead.
question was asked in a classroom. So
Yeah,
in autonomous robotics.
That's
yeah.
what I was also thinking about.
So
Yeah.
yeah, yeah. So as you guys think about that question now, I want to. Another question is like, what are the fundamental like measure or elements of intelligence? Like one and zeros, like like can someone? I think I guess my thinking is that one of the reason maybe we don't have like a good AI right now is because we don't have a good one way to quantify intelligence, and it's not a good way to represent to get down to the fundamental level of intelligence, right? So maybe we're just waiting for someone like Claude Shannon to come up with a theory of intelligence where it can be quantified and measure, and then we will get to a where then maybe we will have an explosion of like AI, right? Similar to like information and the digital age, right? Information theory allow the digital age to happen, and maybe we need someone need to come out with a theory of intelligence for us to have a AI age, right? So anyway, then that's why I was wondering about that question for you guys.
Well, I mean, I think, I guess if we, again, we would probably need to define. So information in this
Yes.
particular case is defined very, very narrowly, right? That is,
Yeah.
so I would say that if we're defining intelligence, it would need, again, to be defined very, very narrowly, because I think we see going back, to 2014 or whatever it was. Like, I mean, we talked about how, like, ants can be intelligent in how they, work as individuals within a collective sort of colony to sort of uphold that colony, provide the resources for that colony, how they move, their bodies, afford that, like, have properties that give them like strength, like that's disproportionate to their size, things like all of that could fall under intelligence. And then, within humans, there's like different dimensions of like emotional intelligence, like it's just straight IQ, like, street smarts or whatever you might want to call it. Like, I mean, I think intelligence would need to be designed much more narrowly. I mean, I think, zeros and one, like, our neurons, like you can say, are zeros and ones, but like every person, like, if you want to zoom in on an individual neuron, like the action potential that, fires for a specific individual depends on like, depends very heavily on that individual neuron within that individual, like, and changes over time. Like, so, and there's like many chemicals and, that go into determining just how one neuron fires, no less. Like, the system fires collectively. So I don't know how easy it is to get like as narrow a definition.
Yeah, I kind of kicking off that, I was going to say intelligence is very much an emergent phenomenon. And yeah, I was also thinking about if you think of it like the one neuron perspective, one neuron is not intelligent, right? People would never say it's intelligent, but obviously when you group enough of them together, they can generate something that we consider intelligent. Um, so it's tough, right? Because if it's an emergent phenomenon, there's not, it makes it very hard to like narrow down like what is the core essence thing, right?
Yeah.
And yeah, talking about our autonomous robotics class, when we talk about ants or neurons, we're talking about like kind of coordination between, small pieces that make up a collective whole. But even when you have animals interacting with the environment, right? And like the behaviors are triggered by the environment, there's this, it's very much like the behavior emerges from the interaction with the environment, which I've already said like 3 times now. But like that also is like a form of intelligence. But again, it's not even like 100%, within the animal, right? Like it relies on signals from the environment for the things to happen, right? So it becomes super complicated because it's not in one place. There's not like one thing. I don't know. And I agree with Mike that you can think of intelligence in a lot of different ways. So if someone does come up with a super advanced theory of intelligence that lets you quantify things, it's going to be one specific type or very narrow meaning of intelligence. It's not going to be the general intelligence we talk about, you know.
Mhm.
Hmm.
I was thinking about like I think in the class, like when you said emergent intelligence, or like yeah, maybe that was the exact phrase, emergent intelligence. Like there was that like turtle bot, or like some type of robot that like basically
Roomba?
well, it was a behavior based robot, and like all it knew was like explore and like stay near like some type of light source or something.
Mm-hmm.
I'm trying to remember. I think those were the
Light
only.
seeking robot, yeah. It's very similar to Roomba, right? Is that
Yeah,
so?
yeah, yeah, exactly. It was essentially like the first Roomba, right? Where it's
Mm.
like explore and stay near the light, and it like covered a decent like it covered like
Mm.
almost like as much area as it could on a single
Just do it
charge.
randomly, yeah. Mm.
Yeah, just doing those two random, like just those were the only two drives it had, but it
Mm.
acted smart because of just
Mm.
yeah the emergent intelligence that of those two behaviors combined. So I mean,
Yeah.
so is that
Anyway.
smart or is that yeah?
Anyway, it's just something I was wondering about as I was reading about Shannon and information theory. Yeah. But in a way, I guess you could argue that, maybe in a fundamental level of intelligence, it's actually just neurons and ones, zeros as well, like the gates, right? Like you measure the computational power of a computer, is like, okay, how many transistors it has on there or something. And maybe we can do similar with, I mean, human brain, right? I think I'm not sure if this is true. Like, is it more neuron you have, the smarter you are, more intelligent you are?
Well, there's
You
certainly
would
a
say?
correlation, but
Yeah, there's correlation. Yeah. So maybe it can actually information theory. Maybe these could be just relaying as a theory of intelligence instead of just theory of information communication, right? So
I
anyway,
suppose.
hmm?
mm,
I mean, but neurons fire like I don't know. Like even we don't even necessarily have like a full grasp on like much about the brain. But like, I mean, everyone
Hmm.
thinks like, oh, certain neurons fire and they're excitatory, inhibitory. But like, then there's like chemical signaling that goes on that like change that. And like, yeah, I guess there's a lot more going on than I think just like a neural network type architecture in there. So.
Hmm. Okay.
I
all
don't,
right.
and I'm not saying that is like if we had enough ones and zeros, maybe we could get at what's happening. I'm not like I believe that's probably true, but at the same time, it's like we're still at too high a level to understand exactly what's happening. So just with ones and zeros at this point, anyway.
All right. So going back to information theory, I would just want to touch on last two uh main thing of the theory is that uh is something about like redundancy, how information he also demonstrated in theory like how information can be like compressed by removing redundancy, which is part of like one of the question he asked, like how to transmit information, like once you define it, measure it, but how do you transmit like information efficiently? And then one thing he showed is to basically compress the information and by removing redundancies because that's human language. That's a lot of redundancy. You can very easily predict like what's because there's a rules right now. What come next up behind another letter or another word. So by removing those redundancy, you basically can send the information efficiently. And another thing, the last thing about his theories, I mean, the question that he answers is how do you transmit information despite noise? Because every channel, every communication channel has a lot of noise. And how do you overcome noise? His theory is that you can actually communicate as accurately as you want over a noisy channel. And the way he do it, proposed that is he proved it. I mean, his theory is that just by encoding your message and on the other end, decode the message, and then you actually can. That's the way where you can transmit information as accurate as you want. given that you actually satisfy the channel capacity, that's also there's a limit to other stuff. But basically, that's what his theory he says that actually the code exists, and from there, all the engineers basically took that and then come up with different methods of encoding, decoding, like all these like we talk about the Perry bits and the Hamming coding stuff like that. Anyway, so that's why like doesn't matter what kind of your how noisy your there's a mathematical equation where you can to calculate how you can transmit this information. So yeah.
Hmm.
I got to implement Hamming encoding back my second
Did
year of
you?
college. So I did.
Hmm. Nice.
But
Oh,
but I will say I'll be redundant and say like to understand redundancies requires understanding what is in the message.
yes. Yep. Then that's why like, we can it's always very like human communication is I mean language is very predictable. You can have rules, right, to like the grammar or whatever to predict like what's the next word.
Mhm.
Yeah. Anyway, so next, so we so far we touch on his two biggest contributions, master thesis and information theory. And of course, we only touch like the surface of information theory because I don't understand information completely. I haven't really dived into it, even though I study like the communication class in undergrad. I actually study some of the stuff, but I forgot everything already, and I did not really use it. So, and I did not understand it when I was studying it anyway. So, um, one thing I wish that I wish I had read Claude Shannon when I was like as a before I study all this stuff. I would be more motivated to do it. So um anyway, so the last thing, actually, last couple of things I want to go over actually is his his work is that he always follow his curiosity. So curiosity actually his main driving force of his all work, and I'll say that's the secret how he did great work. Also how he lived his life too. And so basically in 21 years old or 23, I think 21, he created a master thesis, right? Published a master thesis that revolutionized the digital computing. And like in the age, like maybe probably 10 years later, like 30, maybe 32 or something, he published the theory of information. And after that, he basically just like abandoned the field almost. Like he just like work on something else, right? I think a lot of researchers and he's like always like maybe focus on specialization, deep into really one field. But I think a lot of researchers now also what do you call that in really favor like different even robotics, right? It's fundamentally very multidisciplinary, right? So anyway, so he was doing that a long time ago, and he's uh so he basically just followed his curiosity, and then there's multiple things that work on. So to quote from the book, this is from Shannon actually. I think the history of science has shown that variable consequences often proliferate from simple curiosity. But Shannon's curiosity was different. He's kind man asking a question and then construct usually with hands a plausible answer. Could a robotic mouse navigate its way through a maze? Build one and find out. What other people call hobbies he thought of as experiments, exercise in the practice of simplification, models that file a problem down to its barest interesting form. He was so convinced of a machine-enabled future and so eager to enable its boundaries that he was willing to tolerate a degree of ridicule. Right. So actually, here, so he, I guess, the point is that he very much a theorist, right? Mathematician, right? But he's also an engineer, and he actually liked to build things with his hands. So he spent his rest of his life just like tinkering and do like build stuff. And his house is called Entropy House, and then he has a gadget room, like his toy room. He actually build all kind of gadgets. So that's the one. Have you heard of the Ultimate Machine?
Ultimate Machine?
Yeah. So he built something called an ultimate. He called it ultimate machine, I think, and then he basically is the machine that you turns it on, the arm will pop up and turn itself off.
Oh,
So
I think I've seen is that I think I've seen ones where like it's like a box with a switch and you hit the switch and the box opens up and a little lever turns this.
yeah, something. So he built a machine called ultimate machine. It's kind of a joke, right? So he's very much playful, and that's why the book is called Mind and Play. And then he actually in the gadget room he has like a foam shoes. You like if his neighbor usually see like Shannon actually walking across the river. It's like almost like Jesus falling on water because he built a foam shoes that actually like enable him to walk on water. And then also he also built a mouse that actually solved a maze. It's a first demonstration of actually robot was able to like solve a maze. Which I didn't know that Shannon actually was very much a roboticist, right? So he also built a like robot actually juggles. I was like, oh man, this even right now, a lot of robot like you see on demonstrations, like, oh, okay, robot juggling. I was like, oh yeah, Shannon had done it like 50 years ago, right? So and then also he construct all unicycles, right? He is famous for like actually, used to work in Bell Lab, and he was famous for like just riding unicycles down the corridor, the hallway, and juggle at the same time, right? And Matt, I know you are very super into juggling. You can juggle too. So
Yeah.
yeah, you
If only he lived long enough to get an electric unicycle.
yeah, yeah. But he not only actually like study, he not only like play with juggling, he actually wrote a paper on juggling. So yeah, he published a paper, so you can read it if you want. So and then that's why I think that's why he built the robots to actually to juggle because he always like he start with the curiosity and then ask the question and then think about it and come up with a theory, right? And then he
Hmm.
actually builds models like to have a simplified model to answer the question to see what works or what not. And he's very good with he built he also I built he I think he might have a paper on unicycle too, or maybe I think he have a paper on unicycle, but his paper on juggling did not actually completely finish. I think I might have get it reversed. So in the way he studied unicycle is actually he was asking, okay, what's the smallest unicycle can be constructed and still rideable, right?
Okay.
So what he does, he have a theory of mathematical equation again, but then he also construct like multiple unicycles to test it out, his theory. So I think that's why that's one thing I kind of admire about Claude Shannon because he actually thinks in abstraction, but then also experiments in physical models in physical worlds, right? And then he also worked on the first. He's also a very good chess player, and he actually created the first like chess playing computer.
Mm.
That is actually like now like we all heard about Watson, not Watson, but chess playing computers and stuff like that. But Shannon was the first one that uh, did that. And another interesting thing is before do you think roulette wheel, like gambling, roulette wheel is predictable, Matt?
Pre-
I think you talked about that before because you are very
Do
good
I?
roulette player. Yeah.
I am a good roulette player, but I don't think the wheel is predictable
How would you
generally.
predict it?
How would
I
I
mean, yeah. So
predict it?
wait, hold on. You don't think it's predictable? Can you predict the roulette? What about
I
you,
would.
Mike?
Yeah. I mean, is this the guy who had like something in his shoe to like time it or something?
Exactly.
Okay.
So actually, the ideas did not came from. It's a collaboration with Claude Shannon. So basically, there's another professor at MIT called Ed Thorpe. So uh he came to he basically worked with Shannon to build the first variable computer to predict roulette wheels. Now the reason that actually Ethel say it's predictable because it's physics, and also either way, I think he has a good argument that either way it can be done, that you can benefit from try to predict it. Even if it's physics, if you cannot predict it, using physics you can predict it. If you know that it's not predicted by physics laws, then you can still know something about it to actually make a bet somehow. So I think that's I don't remember his complete argument. So a lot of people believe he's not. But anyway, so Claude Shannon worked with him to build a computer. He of course experimented a lot, and then he actually went to an actual casino to uh to test it out. So
Did it
however, I
work?
think what
Did it work?
he did not work as I think he works. Uh, Actually, I think it's unproven because during the experiment, like the wires, all the wires that keep breaking, so they have to go back in the hotel room, solder the wires together. So they did not have enough testing to prove that it actually works. So unfortunately, but it was the first, I'll say, it's the first like variable computer, right? So so yeah, Shannon and Ethel created that. So that's another interesting aspect too.
Yeah.
All right. So last thing I want to cover is his investing track record. So he actually had the one of the best. So uh, once he studied all theories, then of course the next topic that he was really curious about is star market. Now, can you predict star market, right? Can you make money based on that? So anyway, so that's why he studied. That's one of the reasons that he studied it, and he became really rich. But anyway, so here's a quote from the book. In 1986, Barron's ran an article ranking the percent in the recent performance of 77 money managers. Claude Shannon, though not mentioned in the article, had done better than all but three of the pros. The Barron's money manager were mostly firms with up to 100 people. Shannon worked with his wife on a decrepit Apple II computer. Now, August 11, 1986, Barron's reported on a recent performance of 1,026 mutual funds. Shannon achieved a higher return, 125 of them. When Warren Buffett bought Berkshire Hathaway in 1965, it was trading at $18 a share. By 1995, each share was worth 24K. Over 30 years, net represent a return of 27%. From the 1950s through 1986, Shannon's return on his stock portfolio was about 28%. So the point is, Shannon is a better investor than professional Warren Buffett, right?
Hey,
And then yeah, and then that's his quote. I made money on the stock market. I don't make it by proving theorems. Shannon once famous told Robert Price. And asked what sort of formation theory was best for investing. What do you think his answer is?
insider information?
Exactly.
Is that what he said?
That's
Yeah.
exactly what he said.
Oh no, I totally just guessed that.
Yeah. Yeah. So yeah. Um
He said become
anyway,
a
so that's another reason I like him too, is because he's always like he has a lot of views like on like machines and like how he of course was asked a lot like because he built the I think the mouse the maze solving robot was covered in like Times magazine and stuff like that. It's like I think the name's called Thesis or something like that. But anyway, so a lot of people have got asking about future of AI machine stuff. If it's possible and what he thoughts on that. But you can read on that yourself. But pretty interesting. Anyway, yeah, pretty interesting guy. So he's yeah, that's why in the book he's like a mind play. He's always like very playful with his work. He's never like focused on publication, right? After he published like the information theory, he's like his output of publication almost like just drops because he's focused. I think one time he says like he always like to follow his curiosity and try to answer the question. But once he get to the bottom of the question, right, he's just very lazy, like just publishing stuff. So writing it down, like publish it, share it with other people. Once he know the answer, he doesn't feel the need to like publish and perish like all academia was doing. So um anyway, so I guess I like because I want to cover one last thing about Claude Shannon is lessons I learned is he have a talk about how to approach problem solving, right? So I just want to quickly summarize his because he has a very unique way of not unique way, but very good. He's very good in solving problems basically. And there's a lot of people, and I say his colleagues, other professors, right, very smart people. When it come to him, and they always say, "Oh, he has a way of like distill the problem, like the question, like whatever your problem is, he can help you actually like get into the core of the problem, like simplify it, right? So that way you can answer it very quickly. And his method, his way is method of problem solving is simplification, simplifying the problem, right? Which you guys probably know already. So anyway, so the second step, so first simplification, second step is encircle your problem with existing answer to similar questions. So basically reason by analogy, right? Find similar problems, see how they will solve. Maybe you can solve it in the same way. And the other one is if you fail on both the simplification and solve by similarity doesn't work, you can also try like changing the words, change your viewpoints, maybe change. So maybe now if you have a question, maybe change your question, change your words, and maybe you find out different way of looking at a problem, right? And then the other way is, let me think. Find Fourth is mathematicians have generally found that one of the most powerful way of changing the viewpoint is through structural analysis of problem, breaking the overwhelming down into small pieces. Okay, breaking things down. Okay, yeah, we talked about that before already. And the other thing, the fifth approach is to by inverting the problem. The problem can be analyzed, might still be inverted. If you can use your premises to prove your conclusion, just imagine the conclusion is already true and see what happens. Try proving the premises instead. Um, that's what Charlie Munger's favorite way of solving problems. He always say inverse, right? And recently I also heard like a lot of people like approaching robotics field, and there's a big debate between humanoid and like humanoid robots or special purpose robots, right? I feel like the debate is really not is not is not it's not good debate. It doesn't matter. It's all robots, right? So, but another thing that I heard people mention, okay, the reason that humanoids, if you is people try to imagine what's the future going to be, right?
Mm-hmm.
And then Elon Musk and all the other humanoid, founders, oh, okay, in the future, it's going to be populated with humanoid robots, right? So basically going back, now how can we make that reality true? That means we need to start building human robots now, right? So um, that's one way of solving a problem. And then the other one, the last one that I think once you found your solution by one of these methods or by another, take time to see how far you will stretch. So yeah, you simplify it or you find a solution. Basically, you try to generalize it. How do you stretch the limit of your solution, right? So I would say almost in the information theory, like have no limit right now. Still, people are still studying it, using it, applying it to everything. So generalize to a lot of stuff. Anyway, so last quote. I think that good research workers applies these things unconsciously. Oh yeah, that's not really. I don't need to go through it. So okay. Uh, yeah. I'll say that's the end of my rambling today.
All right. Claude Shannon, most underrated scientist of the 20th century?
Yes.
Yes.
But
Well, is that a question or a statement? Are you asking me?
I don't know. It's
the
the
episode
information's
title, that's
unknown.
what it is.
Sorry,
What?
what?
It's the episode title.
Yes. Yeah. Yeah. I think yeah, anyway, so that's why that's at least that's my view, that he's the most underrated scientist of the 20th century, if not all time, right?
Mhm.
Yeah.
I respect that. He could have probably, with having such an influential paper, he could have easily stayed in academia and like kept publishing things. And even if they weren't that important, he would have had enough prestige to like,
Hmm.
get funding and work. But he was like, nah, I don't care. I'm just gonna move on to other stuff.
Yeah. Yeah. Exactly. Yeah. He just followed his curiosity. I think that's probably the most important lesson, and that's the most. I think that's probably the best way or best secret. It's one of the secret to do great work, right? He followed his curiosity and he did great, information theory, all that stuff. So yeah.
Yeah.
Also, I think make you a lot in the book. He's also saying like he just have fun. He just has so much fun doing stuff, right? Tinkering, right? He just spend his every day is building stuff, tinkering stuff, answering questions. So I think that's the most admirable part. You know, I'm jealous as well. So yeah. Any last thoughts from you, Mike and Matt?
No, I mean that's a good point. Like I feel
Okay.
like I used to tinker more than I do, so this should be,
Yeah.
motivation to tinker more.
Yeah. Just look at him. Like he was he actually doesn't really care money a lot, right? So I think there's a story where like people will find checks in his like MIT office in his drawers, like never cashed, because he doesn't really care about it. But somehow he became one of like I think he became very rich because he was like just follow his curiosity and on a he was not looking for fame, but the fame came with it, came for him too because he would just follow his curiosity, and the money came to him too because he was follow his curiosity as well, right? Yeah, and yeah, do you agree he's the most underrated scientist of all time?
The
Can you think of
20th
something about
century or the all
what
time? The 20th century or all time?
all time?
Oh man, I don't know. I mean, the first guy to come up with fire. I mean,
Okay,
That's
we
good.
might
Good, good point.
not know his name, but that
yeah,
guy's pretty famous. So
yeah. Well, I mean, what criteria are we going underrated?
I don't know anything. I mean, it's a question. It's not really, that's not really a answer question. Yeah, so it's
Yeah.
a provoking question, not a real question, I would say.
yeah.
Hmm. Also, he probably doesn't even care. So
Well, he is dead, right?
yeah, yeah,
Uh,
yeah,
There's the end of the episode. Just cut. He's
yeah,
dead, right? Yeah.
yeah. Anyway, yeah. All right. That concludes the main topic. We want to end with someone put hiker's rule here, like the hiker's rule quote. Don't step on what you can step over. Don't step over what you can walk around. Uh, who's that from? It's not from one of you guys?
Wasn't from me.
I
Okay, I guess it's from me now. I just put it on here. I guess forgot about it because we haven't done Junto in a long time.
I thought wait a minute. So who was saying that? Who said that quote?
Oh, hiker's rule? I think I just
Oh,
got it from. If I probably just got it from some internet somewhere.
oh, okay.
Some information, yeah. Don't step over what you can step. Don't step on what you can step over. Don't step over what you can walk around. Hiker's rule. Anyway, just something to remember, I guess.